The next type of work problem that I want to think about has to do with gravity. Now, in previous courses, you've probably worked problems like this. You've got an object sitting on the ground. It weighs 100 pounds. That's the force due to gravity that's acting on the object. You lift it 50 feet straight up in the air. The work done is the force, which is the weight multiplied by the distance. So you end up with 5,000 foot-pounds. There's a little problem with this, though. It's not really true that the weight, which is the force due to gravity, is a constant. What is presumably true, unless you're adding to the object or splitting chunks off of it, is the mass is a constant. The mass is a measure of how much matter is in the object. Weight is the response of the object to gravity. Mass, unless you're splitting chunks off or adding to it, is a constant, but weight isn't. So really, when we get up here, the force due to gravity up at the top is no longer what it used to be. It's no longer 100 pounds, it's less than that. In the kind of problems you work in pre-calculus classes, for instance, you ignore this fact, but we're now not able to do that anymore. What's really true, at least to an excellent degree of approximation, is Newton's law of gravitation, which was developed hundreds of years ago by Isaac Newton. Newton's law of gravitation says the force on an object due to a massive object is, firstly, proportional to the product of the masses. Secondly, inverse proportional to the square of the distance between the centers of the objects. And three, points along the line segment that connects the centers of the two objects. So I could think of having two objects with masses, m1 and m2. What Newton's law of gravitation says is that the force is some universal constant that doesn't depend on the masses or the distance, multiplied by the first mass, multiplied by the second mass, divided by the square of the distance between them. We're going to be thinking about situations where one of these two objects is hugely more massive than the Earth is. For example, the other mass, that is, the first mass, m1, might be the mass of the Earth, and the second mass, m2, might be the mass of a rocket that we're launching or some sort of projectile. We're going to assume that our masses stay constant and see what we can figure out. But again, weight, don't get confused, is the force due to gravity. It's measured in pounds or newtons if you're metric. The mass is the amount of matter that's measured in kilograms if you're metric, or the bizarre named slug unit if you want to use British imperial units. And as I said, we're going to assume that the masses don't change. Bits are not falling off of our objects or anything. This means that I can sidestep the whole g times m1 times m2 thing and just say the force is going to be a constant divided by the square of the distance between the centers of the objects. This is very much in the spirit of Hooke's law, but it's not Hooke's law because it's not force equals a constant times the distance. You'll have to suffer my atrocious drawing of the Earth, but I'm going to imagine I've got some object. It has a mass, which I'm not worried too much about at the moment. It also has a weight at the surface of the Earth. We're going to lift this object upwards until it's x units from the center of the Earth, and we want to figure out how much work is involved. So this time, the letter x is not going to represent the displacement from equilibrium of a spring. It's going to represent the distance of the object from the center of the Earth. So x is going to start off life being the radius of the Earth, and then we'll experiment maybe with putting different ending values in. The radius of the Earth is about 4,000 miles. Imagine you've got a surface object and it weighs 3 tons on the surface of the Earth. We're going to lift it upwards 10 miles. We want to figure out how much work was done. Now, when we were doing Hooke's law, we would say stuff like, it takes 10 pounds of force to stretch the spring 3 feet. We don't get the work by multiplying those numbers together. What we get was the spring constant. So when x is 4,000 miles in this case, the force is 3 tons. The way we use that is Newton's law of gravity says the force should be a constant divided by x squared. I've told you what the force is. I've told you how far from the center of the Earth you are. So 3 needs to equal k divided by 4,000 squared. Obviously then, k is going to be 3 times 4,000 squared. The units are kind of bizarre though. The 3 is in tons and the 4,000 is in miles. So really, I should say this is in miles squared tons. Here's the thing. I don't actually need to figure out what k is at the moment. It can wait until I need to use it in evaluating something. Now, we started on the surface of the Earth. That makes the distance to the center 4,000 to our degree of approximation. We lifted the object up 10 miles, so it's now 10 miles further away from the center of the Earth than it used to be. B is 4,010 miles, and A is 4,000 miles. So taking my force relation, doing the antiderivative, sticking the B into it and the A into it, I'm ready to evaluate the amount of work needed. I got my calculator out and did all these calculations. It turns out that the amount of work you have to do is 29.92, except it's in really odd units. It's in ton miles. But that's really not much of a problem. I know that 1 ton is 2,000 pounds and 1 mile is 5,280 feet. So every place I see the word ton, I'm just going to replace it with 2,000 pounds. And every place I see the word mile, I'm going to replace it with 5,280 feet. And having done the arithmetic, it takes a whole bunch of energy to lift this object 10 miles up into the air. It takes 315 million foot-pounds, roughly speaking. Suppose you've got an object on the surface of the Earth. It weighs 1 pound, and we're going to move this from its initial position, x equal radius of Earth, to x equal b. I want to figure out how much work is done by doing that. As before, this is easy to integrate. Antiderivative is negative k over x. I have to evaluate that between b and the radius of the Earth. Simplifying the algebra, the work needed turns out to be the constant k divided by the radius of the Earth minus that same constant divided by b. And here's where things begin to get a little weird. If I let the b tend to infinity so that I'm making the object go further and further away, the amount of work, well, this doesn't depend on b. And as b tends to infinity, this tends to 0. I can move this object an arbitrarily large amount away from the center of the Earth just by giving it this much energy. I actually am going to go all the way back to the universal constant g times the first mass times the second mass over the radius of the Earth. I'm going to think of having the small object, small mass object, mass of m2. I'm going to give it this amount of energy, and I'm going to give it that amount of energy in one big push. The kinetic energy is going to be 1/2 m2v squared, and I want to make that equal to or bigger than this critical energy that we're talking about, constant over r sub e. You can divide an m2 out. The conclusion that we're going to come to does not depend on the mass of the small object. You can multiply through by 1/2 and find out that v squared is 2g times the mass of the big object divided by the radius of the Earth. Then take the square root, and you found this critical velocity beyond which the object will move arbitrarily far away from the center of the Earth. Cavendish did an experiment hundreds of years ago where he determined that in modern units, in meter kilogram second units, this universal constant g is 6.67 times 10 to the negative 11 power. The mass of the Earth is about 5.98 times 10 to the 24th kilograms. The radius of the Earth is about 6.4 million meters. So if I take all of these numbers and stick them into this formula I got and do the arithmetic on my calculator, it turns out that this critical velocity is about 11,000 meters per second. There are 1,609 meters in a mile, so 1 meter is 1/1609 of a mile. There are 3,600 seconds in an hour, so 1 second is 1/3600 of an hour. Every place where I see the word meters, I'm going to write this in instead. Every place where I see the word second, I'm going to write this in instead. Simplify the fractions. We're about to get this critical velocity in miles per hour. Do the arithmetic. This critical V value is about 24,978 miles per hour. People usually just say 25,000 miles per hour. This is what's called escape velocity. If I'm near the surface of the Earth, neglecting air resistance and stuff, of course, if I throw an object straight up with this speed or more, it's not going to fall back down. It will achieve arbitrarily large distances from the center of the Earth and never come back. So I often say things like, this isn't exactly rocket science, but this kind of is. So this is what I wanted to tell you about gravitation. I hope this is all clear enough, and I'll talk to you again soon.